In this section, we're going to talk about a particular kind of probability distribution called a binomial probability distribution. And the key here is it has only two possible outcomes, success and failure. Before, we looked at situations that could have more than just two. For example, when we looked at a selection of 5 babies and how many of them had green eyes, well, we had 0, 1, 2, 3, 4, 5 for 6 possible outcomes. But the key here is that we can have only two possible outcomes, just success and failure. All right, a little bit of vocabulary. We have probability of success, P, lowercase p. Probability of failure, Q. So 1 minus P equals Q, or they are complements, P and Q. They have to add up to 1. Number of trials is N. X is the number of successes. X has to be between 0 and N. Please note there has to be a fixed number of trials. That's what our N is. All the trials have to be independent, and the probability, the P, has to remain the same for all those trials. We have a formula that we can calculate our probabilities. It's based on this equation, which, note, this is our combination formula that we had, we could use with our calculator. And then probability of success, X times probability of Q, N minus X, or the rest of the times. So some of them are successes, some of them are failures. Multiply all those together and we get our probability overall. Consider this experiment. So we have 5 offspring, P's. They're generated from 2 parents, each having a green-yellow combination. Because of that, the probability of success of having a green plant, a green pod plant, is 0.75. What is the probability of getting exactly 3 P's with green pods, which means the other 2 would be yellow, out of the 5 that are generated? So N is 5 because we selected 5 of them. X is 3. P, chance of success of having a green pod, is 0.75, which automatically makes Q 0.25. Again, these two have to add up to 1. So plugging them into our formula. And again, this is just showing you the 5C3 that you could use your calculator to do. 0.75 cubed, because we wanted 3 successes. 2 of them would be left, 5 minus 3. Chance of not having the green one, having a yellow one, 0.25. Multiply all those things out, and we get just over 26% chance of having exactly 3 green pods. Now, let's look at a second case. In this one, we're going to use a table instead. Consider the fast food chain McDonald's has a brand name recognition rate of 95%. So 95% of people in the world know McDonald's. Assume that we randomly select 5 people. What is the probability that exactly 3 of those 5 would recognize McDonald's? What is the probability that 3 or fewer would recognize McDonald's? We're going to use our table. So in the back of the book, Table 2, in the appendix, is a probability distribution, and we want to use the 5 case. So let's look at this table for a moment. Okay, so on the side here, we have N, the number in the selection, the number that are being selected. X is how many of those fit the success case. In this case, we're looking for 3 out of the 5. Across the top are the probabilities. So we're looking at the 95% case, 95% recognition. Okay, the downside of the table is it only has selected probabilities, 0.01, 0.05, and then it goes by tenths up to 0.95 and 0.99. But as long as that's one of the probabilities under consideration, then we can use this table. I believe in the book it goes up to N is 15. So we're looking at the N is 5 case. We want 3 of them. We're going to go all the way across to the 0.95, and it says 3. The probability of 3 of the 5 that would be 0, 1, 2, and 3 is 0.021. Now, how about 3 or fewer? 3 or fewer, it would just be adding up the 0.021, the 0.001, and then the 2 0 pluses. Remember that 0 pluses means that it's insignificant, that it would have even more zeros before we got to a number. And so 0.021 and 0.001 would give us 0.022. And then again, using the table, we got 0.021 for the 3 case. If we wanted to add up the 3, 2, 1, and zeros, we had 0.021, 0.001, and then we would end up with 0.022. Now, we could have done this calculation using the equation that we did up above. It turns out that we would have come out with 0.02259, a few more decimal places using the calculation. The difference between the table and doing the formula would have been basically a rounding error, because we came out with 0.022 to 3 decimal places. This would have been 0.023. That's not going to be a significant difference most of the time. I believe the table in the back of the book actually goes to 4 decimal places. The table I just showed you is to 3. Depending on the source, your tables might be a slightly different amount. It's not going to be significant. Now, again, note that in the table, some tables will have 0, some tables will have 0 plus. It does not mean exactly 0. It just means that it's not a significant amount. It means that it's less than the 0.001 in this case, or in the book, it might be less than 0.0001. Considered insignificant, but that is not the same as being 0. Alright, so let's look at some situations in which we want to determine whether or not using a binomial distribution, whether it's a table or the formula, is the right thing to do. So in other words, is it binomial? So, treating 863 subjects with Lipitor and asking each subject, how does your head feel? Would that fit a binomial situation? No, this one would not. How many different ways could you answer the question, how does your head feel? Feels great, feels okay, I don't know, I have a headache. I mean, think about how many different ways. So, by Rule 3, we can only have 2 different outcomes, success or failure. This would not be a situation that's binomial. Okay, let's look at a couple of more cases. Determine whether or not the given procedure results in a binomial distribution. If not, why? We're treating 152 couples with the Y-sort gender selection method. The Y is to have a girl. And recording the gender of each of the 152 babies that were born. Yes, this would be binomial, X or Y, boy or girl. How about we select 15 different state governors, but this is a selection without replacement, and then we record the sex of each one that is selected. Would that be a binomial situation? No, it would not. Selecting 15 state governors, that's fine. That would just make our N is 15. The problem is the without replacement, because once we've made one selection, then there would only be 14, and now our probabilities would change. We would have to do a with replacement for it to be the same probability in each selection. Alright, now let's try this. We're going to have a multiple choice quiz. It has 6 questions, each with 4 possible answers, A, B, C, D. Assume you guessed. So, using the multiplication rule, find the probability that the first 2 guesses are wrong and the last 4 are correct. And again, since we're guessing, and all 4 answers therefore would have an equal chance of being correct, but only one of them is correct, The probability of a wrong answer, 3 of them are wrong, would be 0.75. The probability of a correct answer would be 0.25. And therefore, the probability of having 2 wrong guesses and then 4 correct guesses would be 0.75 squared, 0.25 to the 4th power. It would be 0.00220. Next, make a list of all the possible arrangements of 2 wrong answers and 4 right answers. This particular was the first 2 were wrong and then the other 4 were correct. But what are all the possible combinations of 2 wrong answers and 4 right answers? And for that, we can list them all out. There are 15 possible permutations. Remember that we use permutations when the order matters. Since we want all the different possibilities, order matters. So for instance, the first 2 were wrong and then the 4 correct. That's what we were looking at. But we could have the first one correct and then 2 wrong and then 3 correct. Or we could start splitting them up. Or we could end up with a case in which the first 4 are correct and the last 2. All of these would have the same probability of being correct, or the same probability of 2 wrong, 4 correct. In other words, all of them would be 0.0022. 15 different ways. Alright, now we're going to use our table. Find if n is 5 and x is 1 with a 0.095, and then we're going to look at n is 14, x is 4, probability is 0.6. So let's look at those. So first off, in the 14 case, again, we want the 0.95. So we're going to go 1 all the way across. Here's the 0.95. Here's the 1 out of 5, 0 plus case. And then n is 14. We want 4 of those. We want the 0.6 case. So there's the 0.6. N is 4 out of 14, 0.014. So using the tables, this one came out 0 plus, which means it's less than 0.001. This one came out 0.014 using the table. Very fast if you have the table. But again, we could only do that because this one was 0.95 and this one was 0.6. If we had some odd amount like 0.43 or 2% or something like that, we would have had to go to the formula to do our work there. Alright, a few more examples to do. So, first off, there is a 1% delinquency rate for FICO customers with a credit rate above 800. What is the probability that at least 1 of the 12 people given a loan will become delinquent? Should there be a delinquency plan? Now, we can make the calculations. And here's what we would calculate to 4 decimal places. We could have also, because 1% and 12, we have table for that, so we could have done this as well. So here is the table. Again, at the very top of the page, the 1%, the first one we started with. We are looking at n is 12. We did not use the first one because the question was at least 1. So this would be the none case. And so at least 1, 2, 3, then we're into the 0 pluses. Notice when we did the calculation, once we got to 3, we're at 0.002, 0002, so that would be the 0 plus. This would also be a 0 plus. Notice how many zeros. And so we end up with 0.1074, 0.006, and so if we added them up, we would get to 0.1136 for at least 1. Now, using the table, we could have done the none case. Okay, the none case for 12 was 0.886. subtract that from 1 would be at least 1. 1 minus 0.886 would be 0.114. We calculated 0.1136, 0.114, 0.1136, pretty much the same thing to 3 decimal places. So how to calculate at least 1. Alright, finally we're going to look at 49% of working mothers do not have enough money to cover their health insurance deductibles. You randomly select 7 working mothers and ask them whether they have enough money to cover their health insurance deductibles. The random variable represents the number of working mothers, so that's the X, who do not have enough money to cover their deductibles. The 49%, that's the P. You're going to select 7, that's your N. The X represents how many out of that 7. So we want to construct a binomial distribution. So we're going to kind of do what we did up here, but we're going to do it to create the entire table. Then we're going to do a histogram of that table and describe its shape, and then identify any of the random variable x's which might be unusual, not unusable, but unusual. We could still use them, but they're so uncommon, and then explain the reasoning. So here we go. We have 8 total entries because this is the none case, and then 1 out of the 7, 2 out of the 7, 3 out of the 7, up to all 7 out of 7 of the mothers selected. The 49%, that was the chance of them not having enough money, so 0.51 would be the chance of them having that, or I should say the probability of them having that. And then you can see how that works out. Here is our table, so it matches all those. So the none case, 0.009, 1 out of the 7, 0.0604, and so forth. Here is what the histogram would look like. And then unusual values, since we're going to say unusual is less than 5%, that's less than 5%. The one case, that's more. And then on the other end, 0.0494, that's less than 5%, not much, but it is less. So the 6 would be considered unusual, and so would the 7. All of them are less than 5%. Now, because this was 49%, I had to generate it using the formula. But if it had been a percentage that was like, let's say it had been 50%, and I wanted to do 7, then I could have gone to the table, and then this would have been what I would do for my table. Okay, but again, 50% would have been this one here. Okay, and we see what the percentages would have worked out for. But only if it had been 50%, since it was 49%, and they're not a lot different. Okay, 0.009, 0.008, 0.0604, 0.055, little different, pretty close with the table, but here's what I would have. And so that is section 2 of chapter 4.